40 Days of Chemistry, part 23, this time looking at 9.2.3 ethanol. The first thing we learned about was hydration and dehydration. Hydration is adding water to ethene to make ethanol, and it's used to make industrial ethanol, which is a solvent. It's a non-renewable process. It's currently cheap, but as we know, being non-renewable, crude oil and ethene won't last forever, so it's probably going to decrease in the future. The way it's done is we use a dilute sulfuric acid catalyst because the water itself won't directly undergo addition reactions with the ethene very readily. Dehydration is removing water from ethanol to make ethene. Now that's not widely used at present, but it's got potential to make renewable ethene for replacement petrochemicals if our crude oil does run out. In this case, a concentrated sulfuric acid catalyst is used as a dehydrating agent because it removes water, and there's some animations of the processes here. Here you've got hydration, you've got ethene, water, and sulfuric acid. The sulfuric acid initially undergoes an addition reaction with the ethene, but then substitutes itself for the hydroxyl group to make ethanol. And then for the dehydration, and in both cases we see the catalyst is used to facilitate the reaction. The catalyst actually takes part in the reaction. It performs an alternative reaction pathway. That pathway has lower activation energy and therefore the reaction rate increases, but the catalyst is not consumed, it's reformed by the end of the process. The next thing in the ethanol topic was all about alkanols. Now alkanols are the family of compounds that have a hydroxyl functional group, and they're given the suffix anol. And if there's more than one isomer, a locus needed before the ol. So methanol and ethanol only have one isomer, therefore there's no need for numbers. But propanol can be propan 1-ol or propan 2-ol. Butanol could be butan 1-ol or butan 2-ol. Pentanol could be pentan 1-ol, pentan 2-ol, and pentan 3-ol, etc. So you do need those numbers there if there is more than one isomer. The reason why ethanol is so widely used as a solvent, though, is because of the rule like dissolves like. Substances will be soluble in each other if they can form intermolecular bonds with each other. Now, ethanol's got a non-polar ethyl group. It can form weak dispersion bonds with other non-polar molecules. It's also got the hydroxyl group, which is polar, and can form dipole-dipole and hydrogen bonds, and therefore it can bond and dissolve polar molecules. So ethanol is widely used in medicines and cosmetics when non-polar and polar compounds need to be dissolved or combined. The next thing we learned about was fermentation. Now, fermentation, the theory, is that glucose is converted into ethanol and carbon dioxide with the action of yeast enzymes. We've got glucose with yeast at about 36 degrees, turns into 2 ethanol molecules aqueous and 2 carbon dioxide gaseous molecules. You need yeast for this process. The glucose solution needs to be aqueous. There has to be an aqueous glucose solution for it to work. At 36 degrees is just optimal for the enzyme function in the yeast. The ethanol concentration is going to be less than 15%, or the yeast will die, and it's got to be anaerobic conditions, so no oxygen. And that's because the fermentation process is what yeast does to get energy in anaerobic conditions. If there's aerobic conditions with oxygen, it will just undergo normal cellular respiration, so it needs to be anaerobic conditions. What we did in our experiment was we had 10 grams of glucose and 100 ml of water with some yeast. We set up an airlock which prevented oxygen entering but allowed carbon dioxide to escape, and we used lime water as our airlock so we could verify the carbon dioxide production, because lime water turns milky in the presence of carbon dioxide. And the whole point of the experiment was to measure mass change, which means to record the mass of the process before and after the fermentation. So there was a mass loss due to carbon dioxide escaping the vessel, so there's no loss of any atoms, but just carbon dioxide was leaving the vessel. We also set up a control with no yeast to measure evaporation loss, which could be subtracted from the experiment. So the mass of carbon dioxide actually produced was the mass lost. Take away the evaporation loss, which is the water loss. From that we could figure out the number of moles of carbon dioxide. And looking at the equation up here, we know the number of moles of carbon dioxide is equal to the number of moles of ethanol, but the number of moles of glucose is half as much as the number of moles of carbon dioxide. So we calculate a whole range of factors from that mass measurement. The next thing we looked at was heat of combustions. It's very important you know the definition of molar heat of combustion. It's the heat released when 1 mole of fuel undergoes complete combustion to produce carbon dioxide and water only. We determine this through calorimetry, which is heating water and measure the temperature change of the water. And the equation you've got to know, Q, or heat released, equals mc delta T, where the mc and delta T are of the water. You can then calculate molar heat of combustion. Molar heat of combustion is the heat released divided by the moles of fuel you burned. Obviously, if you didn't calculate the moles directly, you've got to calculate the moles, and you calculate moles of the mass. 100 moles of fuel is the mass of fuel divided by the molar mass of fuel. Heat per gram is another fact you might know. Heat per gram is heat divided by the mass of the fuel, and you can calculate molar heat of combustion from heat per gram, because molar heat of combustion is heat per gram times the molar mass of the fuel. Just be aware that the Q, or heat released, is the negative or the opposite of the enthalpy change, and the molar heat of combustion is negative or the opposite of enthalpy change per mole, and that's because enthalpy change is defined as the heat absorbed, whereas molar heat of combustion is defined as the energy released. In our experiment, we burned alkanols in a spirit burner, and we heated a fixed mass of water in a metal can. We figured out the mass of the fuel by measuring the change in mass of the burner. We measured the temperature change of the water, and also knowing the mass of the water, we could calculate the heat released and therefore the molar heat of combustion using these equations we talked about over here. There were some errors in the experiment. The two main errors were heat loss to the environment and incomplete combustion. The incomplete combustion, the greater the molecular weight of the alcohol, the more incomplete combustion there was, because longer chain alkanols need more oxygen per mole to combust, and we saw that being sootier, and we also saw that being the greater error between our calculated results and the real results. To improve the heat loss problem, you can insulate the can, put insulation on the outsides of the can. You could put a lid on the top, and we also, one thing we did do was we adjusted our formula to incorporate the heat loss to the actual can by incorporating MC.T at the can as well. To prevent incomplete combustion, all you can really do is use a high oxygen environment. We didn't have the facilities to do that in our experiment. Producing ethanol from sugarcane. This is how we produce our beverage ethanol and how we produce our ethanol fuel in Australia. And there's some critical steps. This flow chart's quite complicated, but the critical steps are: you've got to crush and grind your grain, you've got to extract the sugar using an acid solution, you then got to neutralise the acid and filter out the solid residue. With the filtrate, what you do is you ferment it, because that's going to be your sugar solution. You ferment it, as we said before, 36 degrees, no oxygen with yeast. That produces maximum of 15% ethanol. You can distill it then to 96% ethanol. You can't quite get 100% ethanol from distillation. You get 96% ethanol from that. To get to 100%, you've got to use some sort of drying agent, such as potassium carbonate, or you can use a zeolite filter. One of the problems with this whole process is that the energy required for distillation consumes up to about 50% of the energy you're going to get out of the ethanol at the end as well, so it's highly energy intensive. And because of this reason, there's actually a move nowadays, something quite modern, is to use zeolite filters rather than trying to do distillation. And what the zeolite filters do is actually help to filter the ethanol from the water. And be aware that something that some ethanol plants are doing is the solid residue you remove from the process, which is basically a whole lot of cellulose and things like that. You can actually burn that to fuel the whole ethanol plant as well. Next thing we looked at was assessing the potential of ethanol fuel, which is looking at the future. And being an assess question, you need a few things. You need an introduction to the topic, you need your points for and against, and your judgment. And so the introduction to the topic should be about the current situation, which is fossil fuels. You need to mention that most fuels now are derived from fossil fuels. They're non-renewable, they're running out, and the costs are rising. They also release net carbon dioxide to the atmosphere, which leads to climate change issues. In the for and against, rather than having a separate section just on ethanol, you can work the ethanol facts and figures into the points for and against. You need to say that ethanol is made by fermentation of photosynthetic glucose, therefore it's renewable. It's got more complete combustion due to the oxygen in the molecule, which means you get less carbon and carbon monoxide pollutants. If your energy inputs are carbon dioxide neutral and renewable, that means the whole cycle is theoretically carbon dioxide neutral. We'll talk about that in a second. And also, being locally produced, you've got less reliance on foreign oil. But this whole idea about carbon neutral comes from the fact that to make the glucose in the first place, you undergo this process here called photosynthesis, and that produces a glucose molecule, which is here. The glucose then gets fermented to produce two ethanol molecules. If you then combust two ethanol molecules, this is the reaction here. So if you look at the net result here, the fermentation produced 2 moles of carbon dioxide, the combustion then produced 4 moles of carbon dioxide, giving us 6 moles of carbon dioxide in total. We look back here at photosynthesis, it consumes 6 moles of carbon dioxide, and therefore it's net carbon dioxide neutral, that life cycle. The problems with ethanol, though, the energy inputs mostly for this process, especially distillation, are currently fossil fuel based, so it doesn't completely solve the problem of fossil fuels. You require high energy to distill. Ethanol's got a lower molar heat of combustion and heat per gram than octane, which means you've got to have more frequent refilling or carry more fuel. You need engine modifications to more than 10% ethanol fuel. You've got much lower production volume than current petrol, and also using crops and arable land, which leads to the whole food versus fuel debate. The fact that we've got a major concern about food security and food prices if we were going to use food crops to make ethanol. And that leads to the judgment, the potential of ethanol as a fuel. Now, what I would suggest is that as fossil fuels run out, it'll become more competitive. But even still, we need to increase production volume, and we've got to deal with these issues, particularly the food versus fuel issue. And that's really where 9.2.2 comes in, the potential of cellulose. Because if we started off with cellulose rather than sugarcane, for example, we could, well, first of all, cellulose is more abundant, therefore it's going to increase the volume available, but also we can then use non-food crops to actually make our ethanol as well. So that's where the link to potential of cellulose to be the production source of ethanol. And the next thing we looked at was evaluating current success, which is a little bit different to evaluating potential because we're looking at current success. And it's also an evaluation rather than an assessment, which means you need a criteria as well. The introduction will be the same as the previous. You need to set the scene why we're looking at ethanol at all is because of the problems with fossil fuels. Then you look at the ethanol for and against as well, because evaluations need for and against, but also now look at the fact that how it's being used in the world right now. So my for and against, I'd actually modify a bit, only choose a few, the ones that are relevant to evaluating current success. Things like the fact that it's renewable, it's locally produced, you do need engine modifications, you've got lower production volumes, and it also takes up food crops. Then I'll look at how it's actually being used in the world right now. Now a little note here that Sweden's currently the biggest user in Europe, but two of the biggest players in the world are Brazil and USA. Brazil has what's called an ethanol economy. They've got mandatory E20 to 25 fuel, which means the fuel has to have 20 to 25% ethanol in it. They've got pretty much all the cars are called flex fuel vehicles, which can operate on 20 to 25% ethanol or even 100% ethanol, and that means 50% of all fuel burned in Brazil is ethanol, not fossil fuels. But the thing about Brazil is they've got a very favourable climate for growing things like sugarcane, and they've got large areas of arable land in their country, which means that they've got a bit of an advantage when it comes to ethanol, and not all countries have those conditions. USA is actually the biggest producer of ethanol in the world. They produce 53 gigalitres of ethanol, I think, in 2012, and it's actually 10% of all the fuel in USA, which suggests that USA uses a lot of fuel. But unfortunately, what USA, in America, they actually make their ethanol out of corn, and a lot of that's the distillation processes, etc., is powered by coal, which means it's less efficient than Brazil's process for making ethanol. In USA, you've got E85 and E15 available. In Australia, there's a government-imposed maximum 10% cap of E10 in fuel. There are some flex fuel vehicles being introduced to use E85 fuel, and the government's got a target of 350 million litres per year ethanol use. So we're not really, as far as compared to Brazil and USA, we're not really a major competitor, but we do have a plan for ethanol. And so the criteria, we look at that, the criteria to evaluate current success. First of all, if you're going to consider it a currently successful fuel, first of all, it's got to overcome the problems with petrol. And I think ethanol, yes, ticks both those boxes. But the next thing you've got to ask yourself is the extent of use. Is it actually being used to the extent where you can call it a currently successful fuel? And that then links to your judgment. You've got to decide, is it a current success? Is it a current success as a fuel, or as a fuel replacement, as an additive? Is it successfully globally, or only regional-wide success? So you could definitely say, example, Brazil, definitely a success, but is it a global successful fuel? That's up to you to decide. And that's the end of 9.2.3 ethanol. Next will be 9.4.5 water.